Okay, now we're talking about section 19.2, well, the second part for the module. It may not necessarily be chapter 19 the way we have it for this specific class, but I'm just using that nomenclature to keep with the original textbook to give some relative orientation. Depending on the control sophistication, when something goes wrong, the error message may be easy to interpret or completely unfathomable. Many controls feature operator beacons. When they flash, it's time to start unraveling what is wrong. So you want to be thinking about that. So classes of errors. Today, some controls just tell you what's wrong. Others provide an error code. And with the help of a manual, you must decipher that the type of error, which is not necessarily the reason for the problem. For example, syntax error. You know it's the entry sequence or form. So next, what you do is your investigation. Often when a control error errors out, it stops on the bad line, but not always. So it depends on the type of error. So with time, you'll learn that error codes on your machine. Also, you'll get a sense of what might be wrong from the place in your program where the alarm came on. Alarms fall into a couple different categories. So here are the alarm categories: data entry, missing data, math error, extra data, servo error, fluid error, low, conflicting codes, and radical command. So you can have like a syntax command, it doesn't make sense, and so that would be a data entry. Missing data, an incomplete command or cycle. Math error, you have decimal points or nonsense numbers that it can't comprehend. The data entries, you have conflicting commands or words. For a servo error, it cannot correct the lag. For fluid or airflow, you could have issues with coolant, oil, or pressure. Conflicting codes, there's things that don't align, and so you're going to have to be thinking about your program logic. And finally, the radical command to go beyond the capability of the machine. So we'll go ahead and continue on here. So the next section is operator action during a program run. This unit explains several ways to stay in control, both for safety and for efficiency. On a shop-by-shop basis, there are certain actions you will be granted permission to monitor and perform, such as changing offsets as tools wear, changing the cutter tools when they're worn out beyond limits. For statistical process control, later in this text, that would be chapter 29, outlines a data method of seeing and controlling tools, wear, and other variation issues. Don't miss it. It's a very effective pro operator tool. For monitoring production, with chips and coolant flying and safety shields in the way, it's difficult to see how things are actually going for the run. There are a few good ways to stay on top of this. You can have a split screen with a video camera accessory is a good high-tech option, so you can be actually seeing what's going on way down within the machine when it's actually doing the processing of what you've asked it to do. Other methods of monitoring, the screen graphics would be the next choice, but they don't indicate how the machining is going. They do not show where the cutting tools are in relationship to the work in PRZ. As mentioned previously, sound is a prime control too. You'll soon come to rely on your ears to tell you whether things are or are not going well. For emergency plans, the most critical aspect of producing monitoring is to pre-plan for emergencies. The set point, the point is things do go wrong no matter how well we set up the machine up or how many successful cycles it has run. For example, sand pockets in casting or catastrophic tool failure. At those times, the best operator action only happens if there have been some pre-planning and practice carrying out for the plan. So there's 3-step plans. Emergencies fall into 3 general categories. Something doesn't sound right. It seems wrong, but no outward signs are showing. 2, something is showing: serious noise, smoke, cutter loading, or vibration not seen before. And 3, the big one, an all-out emergency. So those are contingencies we want to be thinking about how to be dealing with. Each category can be halted or prevented with a special action. They are in ascending order of seriousness, depending on how quickly the machine must be stopped. So a single block mode, it completes a command, you can stop it. A feed override to 0 stops the cutting motion. A rapid override to 0, it stops at the next rapid. Slide hold, stop axis, but not spindle. And E-stop stops everything. Note, E-stops may also prevent electrical breaks from engaging, which means spindles may coast to a stop rather than stop quickly. But so be it, you are ducking and covering at this crash level. So that's something you can be thinking about. Okay, I'll pause the video here and then we'll move on to this section.